Hello, good afternoon. How's everyone doing today?
Doing good, doing good.
I want to make an announcement about your grade estimate. So you should be able to see on Canvas, you should be able to see your grades. So in the grades, you should be able to see the scores for each individual assignments, like your pre-lab, your worksheet. And at the end, I'm not sure which the individual student view for you is. At the end, on my end, is they show you the weight for different of the assignments. For example, pre-lab counts for 10% of your grade. So there should be a score of the average of all your pre-labs. And worksheet counts for 60% of your grade. So you should see an average of your worksheet average so far. And as we have more assignments submitted, the score will be updated automatically. The quizzes, we have 3 so far, so that counts for 30% of your grade, and they give you a total. And once we have our final quiz, then all of these will be recalculated. So take a look at what you have so far. Now, if you're missing your pre-lab worksheet, you will have a chance to submit some late work for partial credit. So that's also explained in the syllabus. Take a look at your score, especially if it looks like it's very low. It probably makes sense for you to make up some of the late submissions. All right, so any questions about your grade estimate? Any questions? Now, if you notice anything that doesn't look right, feel free to let me know. All right, if no other questions, let's take a look at the lab we're going to do today. Lab 11 is the motion of objects through fluids. So in physics, when we talk about fluid dynamics, with fluids, we meant both air and liquid. So for this lab, we are doing 2 parts. One part is object falling in air, and the second part is the object falling in liquid. When an object is traveling in fluids, whether it's air or liquid, there is a significant amount of drag force that's acting on the object. In the air, we sometimes also call the drag force the air resistance. The faster the object travels, the bigger of the air resistance we have to consider. Also, air resistance, a lot of our physics problems, we neglected air resistance. You may be able to do that when you're dealing with like a heavy object falling, but sometimes when you're dealing with like an object compared to its weight, the object is very light. So the air resistance may not be able to get neglected comparing to the very little weight the object has. Also, if the object have a very big surface area, like if you have a parachute, of course, we are really relying on the air resistance to slow people down. So we need to sometimes think about when it's reasonable to ignore drag force, when it's not reasonable. So the part 1 of this lab is we are dropping coffee filters in the air. Now you can see coffee filters, it looks like an umbrella shape, and it's also very light. Obviously, air drag plays a significant part in its motion and cannot be neglected. So at the beginning of the drop, we have gravity acting on the coffee filter, so it's accelerating. And as I mentioned previously, as velocity increase, your air drag also increase. So eventually the air drag will have to increase to an amount that equal to gravity. So when air resistance, air drag force equal to the weight of the coffee filters, then you can see the coffee filters will no longer be able to accelerate because all the forces balance out. you have zero acceleration, right? So at that point, the coffee filter will simply travel with a constant velocity going down. So it's accelerating at first, but eventually it cannot accelerate anymore. It will just drop with that constant velocity. And we call that terminal speed. You cannot exceed that speed. So we're going to try to measure how exactly F of the drag force depend on speed. This is our goal, okay? In order to evaluate that, let's take a look at the derivation. So what is the relationship between the drag force and speed? Now we don't really know, so we just assume there is a constant c here and it's proportional to v to the power of n. So this is a general expression that we assume that drag force is equal to some constant times velocity to the power of n, and could be 1 or 2 or 3, no matter what n is. As v increase, right, fd will increase as well. But we don't really know the relationship exactly before we do the measurement. So this here, we take advantage of graphing the log function instead of the function itself. Is, well, okay, so how do we translate a curve to something linear? We can translate that by taking the log of the two sides of the equation. The left-hand side become the log of your drag force. The right-hand side become log c times v to the power of n. So when you're when this is our c times v, you can separate that into log c plus the other one. So log a times b, we know that is log a plus log b, right? So c times v to the power n becomes log c plus log v to the power of n. And this power of n can be changed to n times log v. So you can see that how we change a curve, this function, if we graph it directly, it's going to give us a curve. But if we graph this function, it's going to give us a linear relationship. And you can see if this is our y, this is our x, n will be our slope. So we're going to read what n is from our slope. If our slope is 1, then which means, well, your drag force is linearly dependent on velocity. If your n is 2, then that's to the power of v squared. If n is 3, then it's to the v of 3. So eventually you will have to determine which one of this relationship is reflected by your experiment. Let's take a quick look at our pre-lab. So we try to do a little bit of that practice here. This relationship is exactly what we showed you previously. What if something is c times d to the power of n? We, instead of graphing r versus d directly, we are going to graph log of r and log of d. So this becomes log c plus log d to the power of n. And that becomes n times log d. So you can see that this is my y, and this is x. So this is slope k, and this is y-intercept b, okay? So if you graph your data, and in your data, the equation reads y is equal to 1.998x minus 1.769. So from here, can you tell me what is n and what is c? Are we able to tell? So which one of these tell us n?
N is the slope, the 1.998.
Yeah.
And C is the y-intercept.
Yes. So this is our slope. And in terms of c, I know this is my y-intercept, and my y-intercept is log of c. So I know that log of c is negative 1.769. So you can say, okay, C is e to the power of negative 1.769. Well, you can leave it as this, or you can calculate what that is, but this is what the constant is. So you can translate back to say, well, it turns out R is related to D in this particular function like that. D to the power of 1.998 is almost 2. Okay, so that's sort of the a little math behind our approach. So let's take a look and think about how are we going to measure the drag force in the coffee filter. Now, obviously, we don't know what the drag force is, right? We don't know how much force is acting on the air draft, except if the coffee filter reached terminal speed, we know that the drag force at that time is equal to the coffee filter's weight. We can easily measure the weight of the coffee filters. We can just put it on the scale. So we're thinking, okay, if we let the coffee filter fall for a long distance, eventually it's going to reach that terminal speed. And that is what we do in the lab. So in this lab, if you were to do it in person, you have to step on the table so that you can drop the coffee filter from a very high point. And you use a meter stick, a 2-meter stick actually, and see what is the time it takes for the coffee filter to fall from the top of the meter stick to the bottom of the meter stick. So that you can use that to figure out its terminal speed. Now, the idea is if you let the coffee filter drop from very, very high, then by the time it reached your meter stick, it would have already been in your terminal speed. It's already traveling with a constant velocity. So you can just use your stopwatch to time the time it takes, and use the height divided by the time, you can figure out its velocity. Okay, so that's what we are going to do. We increase the number of filters from 1 to 4, 7, 10 filters, record its mass, and we can calculate its weight. So that weight is equal to the drag force because we have let it fall for a long distance. So the drag force must be equal to its weight when we measure that terminal speed. For each of the number of filters, you will record 3 different trials, record 3 different times, and calculate your speed. So let's take a look at an example of one of those coffee filters together. One second. Let me change my, I'll get back to the video. I was looking at the grade book earlier. This one? Okay, so this is our video. Let's take a look. While doing this lab. Okay, they said a lot of things about video before they taking the data. The thing is, when you're in the lab yourself, you have to use a stopwatch, time it when the coffee filter reaches the top of the meter stick and the bottom of the meter stick, which is right at the ground. But here, since we are doing this digitally, they have already built a digital stopwatch in the video. So, and it's already synchronized at the top. So all you need to record is when the coffee filter reaches the ground at the bottom. You don't have to worry about synchronizing it. Okay, so let's take a look at a couple of these.
Move slow enough through the oil for you to do the start and stop for yourself.
Okay, so that's just one filter. They're going to show us the synchronized stopwatch, okay? All right, so you can see it's already synchronized at the top. All you need to record is what happens at the bottom. So you can see that it's up to you if you want to look at the smaller view on the left-hand side, or you want to just focus on the really zoomed out view where you can see a much bigger the coffee filter at the ground. Whichever view you prefer, just be consistent. Okay, it turned out that if you look at this view, the much bigger view, zoomed out view, you might get a time a little bit later. If you look at the view that's smaller, since you can see the whole picture, you're anticipating the fall, you might stop the watch a little bit earlier. Both ways is fine, but just be consistent. So here we record, okay, for one coffee filter, for the first trial, we record the time of the entire fall of 2 meters is 2.27 seconds. Okay, so now I stopped at 2.56 seconds. They will do 3 of those different trials for each of the coffee filters. Let's do one more. Okay, I think I stopped it a little bit later. So if you're not so happy with your result, you can always start again. So let me start again. I wasn't happy with my recording. Okay, so I get another 2.56 seconds. So I will use those 3 different times for the 3 different trials as the time of the fall. So let's go and take a quick look at our data to see, okay, how do we fill out that table? For each of the time, you'll be able to calculate a different terminal speed, right? So for this time, the speed will simply be distance over time, which is 2 meters divided by 2.27 seconds. So you will put that timing speed here. You can divide it by 2.56 in here. So you can calculate an average speed and then also calculate the uncertainty. So the uncertainty of the speed, we have talked about the, if you have an equation where V is some known number multiplied by, divide by another variable or multiply by another variable, that the absolute uncertainty is simply this number times the absolute uncertainty of delta t. Okay, so that is one of the rules we said in lab 1. So to get the uncertainty in the speed, all you need to figure out what is your uncertainty in your time. So based on these data recorded, what is my uncertainty for time? Anybody could tell us? What is uncertainty based on these 3 data we just recorded? What do you think? Anybody would like to share their thoughts? You can also type in the chat.
I got 2.45.
Okay, so that must be the average time, right?
Yes.
Okay, that is the average time. Very good. What if we want to know the uncertainty? I have a response in the chat said 0.145 seconds. So Neil, how did you get that? How did you get that number? We use the max over a minus min divided by 2 method. Right, very good. So use your the maximum value for your time that you recorded in the 3 trials minus the smallest, you can get uncertainty. So in this case, for what I have recorded, this is my uncertainty, and you multiply that by 2, which will be the uncertainty for your speed, because you multiply by that distance. D is 2 meters. Your data will be different every time everybody record their own data. It will all be different. Okay, so you know how to fill out the table. I just wanted to remind you of one thing about what you see on the video. So they're going to go ahead and do 2 coffee filters, and then 7, and then 10 coffee filters. One thing that is a little wrong is you can try this yourself. You'll see the trend as you have more and more coffee filters. Do you expect the time of the fall to be shorter or longer? Do you have more coffee filters? Do you record shorter time, or do you record longer time? Shorter time. Yes, that makes sense. Thank you. Because it's if you have one filter, the air resistance is much more significant than gravity, right? But you have more, then gravity is more than the air resistance. However, when you record the 10 coffee filter data, you will notice that it's consistently longer than the 7, which is not correct. So if you take a deeper look at that video, you realize that their stopwatch is not synchronized at the top. So when it's all the way at the top, I can't go exactly, I have to be very fast. You can see that when it's barely at the top, it's already 76.76. So the stopwatch is not synchronized. That's why you record a longer time. So I want you to take whatever data you record for the last 10 coffee filters and subtract 0.6 seconds from that, just to correct for that mistake, okay? So if you read 1.65, then you subtract 0.6, you will have 1.05 seconds for your time of the fall. And only do this for the 10 coffee filters, because that is where we notice this mistake. Otherwise, your data will not be as good. All right, so that's all. That's just one little thing you need to be more careful about. And then they weigh the mass for 10 filters. Of course, it's always more accurate when you put 10 filters on the scale and divide it by 10 to get the mass for one filter, right? Because one filter would be too light and maybe your scale is simply not accurate enough. So for 10 filters, you can see it's 16.7 grams. So you can write the mass for one filter as 1.67 grams, and you can multiply that either by 2 or by 4 or by 7, by 4 or 7 to get the mass for each different number of filters, and you can calculate your air drag. So that will complete the first data sheet. There is a question asking, okay, so how much seconds is 0.6 seconds? 0.6, not 0.6, 0.6 seconds that you want to subtract from the time you record for 10 coffee filters. There's a question for average speed. Should we average the 3 speeds or take the average of the max plus mean speeds? You calculate a speed for each of the trial and you take the average of those 3 different speeds. Okay, yes. So we don't calculate an average time, we just calculate the average, calculate the speed for each of the trial and then average those speeds. So that concludes our first part of the lab. Let's go back to look at the second part. The second part is where we drop objects in liquid. Instead of the air, we now have liquid. We have these small spheres that we drop them in oil. Now you can see that there are two types of forces pointing upward right now. You have the drag force that we just talked about. We also have another force, the buoyant force, because we know any object you immerse it in liquid is going to feel this floating force from the liquid. Buoyant force is always there, regardless if you travel or not. And the drag force is only there when you travel in the air. So in this case, if the object have a downward speed, then you're going to feel a resistance, the drag force. So both of these are pointing upward against the direction of the motion. So that is the total resistance, FR, that you will feel. Okay, so this force diagram really just 1, 2, 3 forces, 1 up, 2 up, 1 down. This one is really just showing the overall force pointing in the upward direction. So when the object reaches terminal speed, meaning that the total force upward is equal to the total force downward, which give you 0 acceleration. So in this case, is the sum of your buoyant force and your drag force is equal to gravity mg. Okay, so not just one of them, but both of them. Let's not look at the data sheet. Let's take a look at the theory part. So F of R is the drag force plus the buoyant force. The drag force is now the drag force, as you measure eventually, your data will show is proportional to velocity, c times v, linearly proportional to velocity, and buoyant force is just FB. So you will do a graph. Again, you will measure the weight of these different spheres, because F of resistance is equal to its weight, right? So you measure the weight and you're going to time it so that you measure the velocity. So eventually you will be able to get an equation, again, is x, y equals kx plus b. So the slope will tell you what this constant is, and this b in y-intercept will tell you the buoyant force that the sphere feels. Okay, so we already know how to calculate the buoyant force, right, in our previous lab. In this case, you are reading the buoyant force from your data, which is the y-intercept of your data, and you can compare that by using Archimedes' principle to see if this is indeed correct. So for example, let's go take a look at our worksheet, and then we'll go back to the lab portion. Is okay, now we have a marble sphere and give you the diameter, and we immerse that in oil. What's the buoyant force? You guys still remember how to calculate the buoyant force? Is the weight of the liquid that is being displaced, right? So to calculate the weight, you want the mass of the liquid times little g. Mass is density times volume. So it's the density of the liquid, which is oil, times the volume of the oil that's being displaced. So how much oil is being displaced is exactly how much space you have to make for the marble. So it's going to equal to the volume of the marble times little g. So you can calculate the buoyant force using Archimedes' principle. This is what you would do in the lab as well, and compare that with your data. So the volume of a sphere is 4/3 pi r cubed times g. So in this case, my little r radius, let's use big R, is half of the diameter, and my diameter is 1/4 inch. Okay, so it's 1/8 of an inch, and 1 inch is 2.54 centimeters. So you can calculate the radius, and you can calculate the buoyant force. So let's go back to our lab. all of these plastic material, all of these different spheres, they're all made of the same volume. So you can just calculate the volume once. They're all of the same diameters. It's just like I showed you. You can calculate volume for them. And excuse me, and they have different densities for these volumes as well. Okay, so you know how to calculate the buoyant force theoretically. And how are we going to measure them in our lab is just as we did last time. For the F of R, the total resistance is equal to the weight of these different objects, right? So for the plastic, it would be the density of the plastic multiplied by the volume of the plastic. And you will put that here and multiply that by G is your resistance force. And that is your Y value. And the velocity will be your X value. And you plot Y versus X. And timing this is much easier because it travels so much slower in the oil. The idea is the same as before. Let's go to the data. So you can see that for the entire fall, you wanted to start recording for 30 centimeters of fall. They had a little rubber band here. You want to start at the top when the marble passed the rubber band, and you stop at the end when the marble reached the base. So let's do one of the trials for a plastic sphere. Okay, so now I'm not recording. I'm not recording yet. This one, they don't have a digital stopwatch because it's very easy to use your own. It's not fast enough. So we're gonna use our own stopwatch. So you can do this with me if you wanna take your phone and get it ready. So we're going to start recording the time as soon as this marble passing through that middle, white ring at the top. We'll start recording. Okay, I'm gonna go ahead and hit play. So right now I started my stopwatch and I'll just wait until it reaches the bottom. You can take a look at the right-hand side. That's the zoomed in view for the marble. This one falls so much more slower. Okay, so it's approaching the bottom. I'm going to stop when it hits the bottom. All right, I stopped right now. What is anybody would like to share their data with us? What is the time they have recorded for the plastic marble? 50.02, okay. And I got another 50.19. I got 50.35. So everyone should, every time you record this will be slightly different, and that's totally normal. So you get these 3 different trials, and you can calculate again the speed. Here you use 30 centimeters divided by the time. So it's going to be 0.3 meters divided by 50.02 seconds. So that would be your speed for the first trial, and divided by another time and divided by another time. You get 3 different speeds. You calculate the average and uncertainty. Again, delta V is D times delta T, and the distance here is 0.3 meters times delta T. Delta T is the same as max minus min over 2. Okay, so that you will be able to finish this data table, and what you want to graph is your resistance force, which equal to its own weight of the marbles versus all the different speed that you have read. Be a little bit careful. The difference between part 1 and part 2 is part 2, we are more interested in getting this constant C and the Boyne force. And we already tell you it's proportional to V, not V to the power of N, right? So for part 2, you just graph your weight and your speed directly. Part 1, once you get your weight and your speed, you cannot graph it directly. You have to take the log and then graph. So that is what is different. So let me show you. Okay, where's my data table? Over here. Well, add separate page. I'm gonna write it here. So in Excel, like I said, there's no need to do this by hand. As long as you know how to do it by hand, then you can just use the computer, which is more accurate in terms of graphing. You will make a column, say that that's my speed, right? You put all these data in here. Make a column for your drag force, which is these data, you put it here. And then you do another new row, log V and log FD, because you're plotting the log of these variables, not plotting them directly. So here you can just do a function, which is equal to the log of this cell, and you do a log of whatever is here, and they can, you can just drag it down and they'll fill it up for you. So what you want to plot is this is your X and this is your Y. And then you will form a scatter plot and they will give you a function. Okay, so just don't forget this step. If you forget this step, then our data will not be correct. For the graphs, we plot the average speed. You can see your plot will have how many data points? 1, 2, 3, 4, 5. 5 data points. You have 5 different Y values and 5 different X values. Okay, so the each of the speed is an average for the 3 different trials. Okay, that represent, these different speeds all represent one coffee filter. So they will show up in our plot just once. Okay, we use the average speed. That's all. That's all we are going to have to talk about for object moving through fluids. We do the coffee filters in air and we do spheres dropped in oil. Are there any questions so far about this lab? Any questions? Okay, so if you think of any questions later on, feel free to email me. Otherwise, I will see you all next week. Okay. And again, make sure that you take a look at your grades, estimate, make up for your late submissions if you can. And if you have any questions, let me know. Okay, I'll see you next week. Have a good rest of your week, everyone.
See you next week, Professor.
Bye-bye. Thank you.